talk about stochastic resetting. And okay, all right. So I showed this picture yesterday, so I'm not going to show it again. So let's go to this. So yesterday, I focused on a search process and the absorption process for finding a target, and talked mainly about what happens when this is a complex process, which is typically non-Markovian. Today, I'm going to focus on the effects of reset on a search process. And this, one of the problems with the reset community is, number one, it's a bit of a bandwagon. People just kind of find any single problem that people have studied and they add reset. And often it's not that surprising what happens. So I've been trying to find problems where it's a bit less more surprising. And also one of the problems has been in the past that it seems pretty unrealistic. So what I want to do today is talk about ways to make it more realistic, and claim that cell biology has plenty of examples of a resetting mechanism. For example, in axonal transport, molecular motor can be detected as being faulty or what have you, and can then be removed from the system, which is like a resetting. And I'll give another example a bit later. And this whole area of using queuing theory to talk about the accumulation resources is a talk for another time, but I wasn't paid enough to talk about that too. Well, all right. So let's just go back to an introduction to the standard theory. So stochastic resetting says that I undergo, let's just look at the discrete time version, I undergo standard Brownian motion, but at each time step, there's a small probability that rather than carrying on with Brownian motion, I reset at some Poisson rate R to a fixed position. That's it. That's stochastic resetting. And what I want to do in the first part of this talk is explain why this is of interest to statistical physicists in particular, and then talk about some of my own work in this area. Okay. So if you look at the Fokker-Planck equation, you have to add, if you like, a removal term, because anywhere in your space, you can be removed from that position and sent to the reset position at a rate R. And this Dirac delta function is conserving the probability because you're resetting to X naught. So it's pretty obvious. The important point and what makes this a powerful, a simple but powerful protocol, if you like, is that if you know the solution of your problem without resetting, it's then very easy to incorporate resetting, but using a renewal process. Because once you reset, you've forgotten where you were before, so you can restart the process. And so this is an example of a last renewal equation that says, what are the contributions to me being at position X at time t, where there are all the paths that never reset, but in order not to reset, that probability is e to the minus RT. So these are is the contribution from never resetting. Whereas this term says that if I last reset at time tau, is that good? Yeah, maybe there's a typo here. Then after I've reset, I don't reset anymore, so I just use P naught. So if I use that equation and Laplace transform it, I end up with this equation. And so if I know my solution to the non-resetting case, in Laplace space at least, I can just rearrange that equation. But the important thing is very quickly pop out of this, that even in an unbounded domain, so you know that you don't have a ergodicity in the unbounded domain in the sense that you don't have a station distribution because point-wise it's 0 in the large time limit. But when you have resetting, and this makes sense because you're not allowing the system to go off to infinity because you keep resetting. And so what you find is, just using this basic result from Laplace transforms, that you have a non-trivial stationary state. But the point is, this is not an equilibrium stationary state. So it's called an NESS. And non-equilibrium statistical physicists are often interested in these sorts of objects. They're stationary, time independent, but there are still non-zero fluxes around, and that's a mark of something that's non-equilibrium. And then you can, of course, you can solve this object, and you basically get in terms of modified Bessel functions. So this was done in 2011, I think, and the handle's been turning ever since. And the handle's been turned mainly by Sanjay Majumdar, I have to say, and also some of his ex-students. Okay. And one of the reasons you can turn the handle is because you can replace Brownian motion by your favorite stochastic process, as long as you know what the solution is in the absence of resetting, and you can take the distribution of waiting times between resettings to be non-exponential, if you like, you end up with this very general renewal equation, which you can then analyze. And so you can apply it to a lot of things. From my perspective, in terms of search processes, what's more interesting for me is the effects of resetting on first patches time problems. So, and this again is the second of the two elements, non-equilibrium steady state, stationary states, and the first patch time problem that has created this interest in resetting. Okay, so let's look at a simple target problem. And I talked about these sorts of problems yesterday. So we have some domain, bounded or otherwise. It doesn't have to be bounded. And we have some target whose boundary is totally absorbing for now. We have a Brownian particle searching for the target, but we now add this extra ingredient that at some rate, it resets to a fixed position, which we can take to be the initial position. What created interest is, as we know, if it's an unbounded domain, in the absence of resetting, and in more than one dimension, the probability of finding the target is it's a transient Brownian motion. So there's a probability of finding the target's already less than 1. And certainly even in one dimension, we know that in an unbounded domain, the mean first passage time is infinite. But when you introduce resetting, it renders the mean first passage time finite. And moreover, for many, many situations, you get a unimodal function with a minimum mean first passage time at some reset rate. And so that's of interest to people because it speaks of the notion of using stochastic search processes in some optimal way. Okay. And again, you can play the same game as for the non-equilibrium stationary density, in that you want to explore first passage times. And one way to do it is to note that if you write down the survival probability for the particle, then if you take the first derivative of Q and multiply it by -1, that is the first passage time density. And so if you then plug that in to calculate the mean first passage time resetting, what you find is it's just simply the Laplace transform of your survival probability, where the Laplace variable is 0. So if you can solve things in Laplace space, that's one of the nice things about looking at first passage time problems, if you're looking at moments, because you can just use the generator of those moments and stick to Laplace space and not have to invert anything. Laplace works. So you have a renewal equation. Again, you break it up into contributions to survival probability that never reset, and those that last reset at time tau. Then after that, so that's the full survival probability, but after that, you don't reset again. So the survival probability for the remaining time interval is given by the non-resetting survival probability, which you can calculate in many cases. Use the convolution theorem, Laplace transform, rearrange, and you end up with this quantity relating the survival probability with resetting to that without resetting. Now take the limit s goes to 0, according to the previous result here, and you pop out the expression for the mean first passage time, which is finite even in an unbounded domain. So this is kind of now classical. So when I often give talks, as I'm getting older, I talk about classical. And does classical mean Greeks? Are you talking about Euclid, or does classical mean Newton? So, and you could say a lot of applied math in the UK has been kind of fluid dynamics from the 18th century, or does classical mean something that was done 10 years ago? So again, it depends on your perspective, I guess. All right. So let's just do this in a simple calculation. So if you take a bounded domain between naught and L, x equals naught totally reflecting, the other's absorbing, you can just calculate the problem in the absence of resetting, calculate the survival probability in Laplace space, then write down the formula, and then calculate the corresponding thing with resetting using that formula, calculate the mean first passage time, take the limit, the L, the size of the mean, goes to infinity, so you're on the half line, and you still get a finite result. And the important point that, the number of papers that have these sorts of figures in, and I'm guilty of that as much as anyone, is exponentially increasing. But basically, because it's a finite domain, there's one subtlety here that, well, let's look at this case. If it's an unbounded domain, you know that as R goes to 0, you get back to no resetting, so the mean first passage time must be infinite. If you take resetting rate too large, you never have a chance to reach the target, so you also get infinity. Interpolate, you get a finite, and it turns out that in many cases, most cases I know of, if not all, you get a unique minimum. However, in the finite domain case, because even without resetting, you can have a finite mean first passage time, whether or not you get a minimum depends on the position of x naught. And so it's a bit more subtle when you go to the interval. But anyway, that's just one example of work done on resetting. So when I got into this, and again, I was unlucky. I told you yesterday about a case where I submitted a paper to PRL, and I thought it was a really nice paper, but it was too speculative because it's as if mathematical physicists are allowed to speculate about black holes, but they're not allowed to speculate about things in cell biology or whatever. So this is another example, but here it was just bad luck because I've been working on other problems using renewal theory and the probabilistic argument I'm going to tell you about, and I then applied it to the resetting case, but it turned out that some physicists had, in a much less elegant way, I should say, Powell and Rubeni and people like that, people in Israel had solved the problem. I thought it was more elegant, but elegance isn't enough these days to get a paper in PRL. All right, so what's the basic scenario? But also I want to tell you about this method because I've applied it to lots of different things. So to be more realistic, instantaneous reset's just not going to be relevant. It's not physical. So what one wants to do is say that once I reset, it takes time for the me to return to the reset point. And let's, for simplicity, assume I return at a constant ballistic rate. And there are reasons to think that's the case. If you're returning a molecular motor to the cell body, you're being transported by dynein. And dynein has an effective velocity, which is approximately constant. So that's a good approximation. In the sort of work I've done on cytidine-mediated morphogenesis and things, the same thing. It's like a shrinkage of a microtubule or actin filament. So that's, I think, a reasonable approximation. The other thing is, and we talked about this a bit yesterday in terms of run and tumble particles, once you return to the origin, there are often situations in which you remain bound at that point. It could be a sticky boundary or something like that. So there's a refractory period, a waiting time before you start the search process again. So both of these are relevant and I think important to include. And so the question is, how do you generalize the renewal theory I talked about, which is straightforward for instantaneous reset when you have these two sorts of delays, finite return times and refractory periods? And so the way I formulated this is as follows. And I'm going to exploit renewal theory and something that is called the strong Markov property. So I'm kind of putting on my probabilistic hat. So let's break up a typical absorption event in terms of the following. And of course, some of these could be infinite or zero, depending on particular realization. But let's assume that the particle resets at least once. Let S be the time it takes to return to the reset point the first time. Let N represent the refractory time that I spend at the reset point before I restart. But then I have no more constraints on R, so I can reset an arbitrary number of times before and get stuck before I find the target. I've just shown 1 and 1 here, but this could happen 20 times. It doesn't matter, that's all lumped into R. So what I'm going to do is now use a renewal argument to calculate these effects. So I think it's a really powerful method. So given that picture, let me define the following first passage times. T is the full first passage time that says, I don't care how many times I reset, I might not reset at all. This is the first passage time, stochastic variable that I reach the target. S is the first time I return to the reset point, assuming I do return at least once. And then R is the time I finally reach the target, given that I reset once and had one refractory period. So those are the times. And I can introduce some probability kind of spaces or event spaces where omega is the set of all events for which I do find the target in finite time. Gamma is the set of events, the subset of events for which I reset at least once. And so omega mod out gamma are the set of events for which I find the target without resetting. So it's a bit difficult when you just have one slide, but if you can kind of just imagine these, remember these objects, I can now do some cool simplifications. So let TR be the thing I'm interested in, the mean first passage time that I find the target, irrespective of the number of resets. I can decompose that in terms of the contribution from paths that never reset, and then the remainder. And if I look at the remainder, it has three components. It has the mean time in which I take to reset once, the mean time for me to be in my refractory period, plus the remainder of arbitrary numbers of resets. And this is where the power of this method, first of all, the mean refractory period is just given by the particular waiting time density I choose. But the crux of this is that once I reset, I've lost all memory of what's happened before. So R has an expectation the same as T. It's TR. And this is called the strong Markov property for this process. So the Markov property says if I have data from various points in past time, the only effect it has on my next state is the most immediate previous time. That strong Markov property says you can apply that argument even if the previous times are stochastic variables, stopping events. And so that's basically what the summary of that. So I now have a nice formula which I can rearrange and determine TR, provided I can calculate all the other objects. But it's quite easy to pop out at least most of these, because I can say, well, what happens if I go back to the instantaneous case? I can start identifying certain objects. So if I compare that with that classical formula for the first passage time for instantaneous reset, it's very easy to show. And you can also show this directly, that the probability of at least one reset is given by R Laplace transform of the no resetting survival probability. Using similar arguments, I can show that the quantity on the top that I still don't know can be decomposed into the bit that would occur if there was instantaneous reset plus the mean return time. And the mean return time can be calculated in terms of the distribution of the probability that when I reset, I'm at a particular position X, because the time to return will depend on how far I am from the reset point, and I'm moving at a speed V. So putting all this together, I end up with this very general formula for the return mean first passage time with reset, where I have this term Q0, which was in the original equation. I have a term that depends on the mean refractory period, and then the remaining term takes account of the fact that I return with finite speed. So this now becomes a powerful method. And I thought it was really cool, and I was really pleased with myself. And that's always, when you're a researcher, especially for younger people, you've got to distinguish between your quiet moments where you come up with really cool ideas, and then try and remember that when you're rejected. Because there are two processes being a researcher. There's when you know you're being creative and doing something nice, but then, of course, there are lots of smart people in the world who are also looking at overlapping problems. And sometimes they'll have already done it, maybe not in a nice, neat way. But don't forget that aha moment you had in the privacy of your own living room or whatever. So I was pleased about getting that. But of course, unfortunately, this formula had been written down using very inelegant methods. And of course, as I said, just like everyone else, I then produce figures of unimodal curves, looking at the effects of finite delays, where the optimal reset point, etc., etc. That can be popped up. Okay. So far, I've just given you an overview of classical stochastic resetting and my contribution to the classical story. Now I want to talk about a concrete application, which I think puts more meat on the bones of resetting. And also, this is an area of research in terms of putting on my mathematical biology hat that I currently have a master's student working on. And I think it's a very interesting story, but it's also relevant to morphogenesis, which is also a topic that came up in this program. What's been discovered in recent years, and Korenberg is the main person who's done this, is that many cells in living organisms, and certainly in embryos, have these extensive thin protrusions called cytonemes that are rich in actin, and they have actin polymers along which myosin molecular motors can walk, that can extend up to 200, 300 microns. Just to give you an idea, this is 30 microns. This is a bunch of cells in the tracheal region of an embryo in Drosophila, imaged in an appropriate way. So that's the first point. So these provide an opportunity of cells during morphogenesis of directly speaking to each other without having to do it using paracrine signaling, you know, by diffusion of molecules. Here's an example. If you're thinking of morphogenesis, what you imagine is you have source cells producing morphogen and making direct contact with neighboring cells via these cytonemes, and the morphogen transports along these cytonemes, and the effectiveness of the transport varies with distance. This becomes an alternative diffusion as a mechanism for setting up morphogen gradients during embryogenesis. And it's amazing because, as far as I know, I'm the only person, maybe there's a reason, maybe it's not that interesting, but I seem to be the only person mathematically modeling this. And it seems to me really important and lots of interesting questions that still have to be addressed. There's been a lot of experiments on this, but very little mathematical theory. Why it's also of interest, and this is what I might try and put in a grant, because I can just say COVID-19 and they just throw money at me, is that it's now been found that these protrusions provide a mechanism for within-host viral infection. So rather than these virions being released into the extracellular space and diffusing, they hijack these filaments, in fact, can encourage them to grow and can then infect other organisms. So how does one mathematically model this as a mechanism for within-host viral infection? And I have a master's student working on that problem. So he's going to cure COVID. Or that's what I'm going to... In the next one, yeah, the next one. That's going to say much. So in my grant history, I've basically developed Skynet and solved artificial intelligence. I found a cure for epilepsy. There are loads of things I've done in, well, I said I do in my grants. Luckily, the NSF never follows up on what you claim you're going. Otherwise, I'd be in prison, I guess. Okay, so now it becomes an interesting stochastic process because, at least in vertebrates, what's found is these don't form permanent connections. They grow and shrink. And if they grow in a direction towards a target cell, they'll find the target cell, but they might grow in a direction in which they fail to grow. So now you can see why reset's important, because if you're growing in the wrong direction, you want to have some non-zero probability, because that's a waste of time, that after a while, you reset and then try again. So this is a perfect, if you like, ground for exploring the effects of reset in a biologically relevant scenario. So that's what I did. So let's just simplify things. Let's imagine there's a single target cell, and of course one can look at multiple target cells and splitting probabilities and so forth, where we have a cytoneme, and that with a certain probability, when it nucleates and starts growing at some speed v plus, it's in the right direction, and it will eventually, if it doesn't reset, find the target. However, there's a certain rate at which you can reset, and then once it resets, there's a waiting time before it nucleates again and starts growing. But the reason you need this resetting, there's a non-zero probability that it might grow in a direction that it doesn't find a target cell. And so then it's just a waste of time, and then it has to return, and then it tries again. This sort of stochastic search and capture mechanism is known to occur during cell division, where you have microtubules from the nuclear spindle, mitotic spindle, growing to try and find binding sites on chromosomes as they're dividing. So this is a well-known mechanism in other contexts. So you see that it's a bit like run and tumble. You have, but in this case, it's with resetting. So it can grow at a certain speed v plus. That's like moving to the right. But in this case, it's continuously switching between rightward and leftward moving. It moves to the right ballistically, but at a certain rate R, it resets, and then it shrinks all the way back to the origin. The origin is just like for the run and tumble particle. There's a bound state, which is the nucleation state. And at a certain rate, it renucleates and starts growing again. And so you can see the link with, and that's one of the things so a lot of people in active matter, they get all excited about run and tumble particles and then active Brownian motion. But there are many other problems in cell biology where analogous things occur. The growth and shrinkage of microtubules, or these cytonines, molecular motor transport. So these velocity jump processes occur in many different situations, not just bacteria moving around. You can write down a system of equations for this. You have pure advection, but you can disappear in the plus moving direction at a rate r. That then leads to shrinking, moving in the other direction. And then you have the sort of equation I wrote down yesterday saying what's the rate at which you build up the being in this bound state P naught given by this equation. And then you have appropriate sticky boundary conditions, which essentially are identical to the sort of things I talked about yesterday. And then I have an absorbing boundary condition at the wall, which is the target cell. Okay. So I can apply exactly the same arguments. I won't go through the details because I've already gone through the general case, but just here, because the growth is also, it's not diffusive now, it's just ballistic, I have the same picture. I reset once, I get stuck before I nucleate, and then I carry on doing the same stuff. I can apply exactly that formula, but in this case, everything can be calculated very easily and explicitly. So if I put all that together, I can then write down my result. But now I have one extra thing. And so I have to decide, I won't go through details because it means introducing more conditioned first passage time objects. But basically, I have to generalize what I've said before, where you can either find the target with without resetting, or you can reset once and then reset again. So that's one possibility. So if you look at the right-hand side, if Z is 1, that's what I talked about before. But now I have a possibility that when I'm in the nucleating state, I go in a direction in which I don't find the target and have to come back again. You can apply exactly the same mathematics to this more complicated problem. You just get this extra term in here, which has a neat interpretation in terms of a geometric series that, or kind of, it's because you've got a Bernoulli process at each stage with a probability Z, you'd go in the right direction, and a probability 1 minus Z, you go in a false direction, and that can happen multiple times, so you end up with a geometric series. This all pops out of the renewal theory. Okay, so this is quite a powerful method. And as I said, you get paid $100 every time you publish a paper with a unimodal curve. You can do the same thing for this problem. So resetting isn't just a game played by statistical physicists. It's interesting, but has no applications. There are concrete processes in cell biology where these sorts of ideas, I think, have relevance. You can also extend this to multiple targets. It gets more messy, but you now have to introduce more conditional first passage times that I grow in an appropriate direction, and it's towards the jth target. And so, and it becomes a bit more messy, but you can apply exactly the same things. you can calculate splitting probabilities and mean first passage times. And so, for example, the splitting probability for this simple problem is quite easy. Zj is the probability that you grow in the j correct direction. You've got a factor to do with the fact it takes time to reach the target. And basically, you get a straightforward formula for. Because if you like, the splitting probability doesn't care about time, so it doesn't really care about how many times you reset. So that doesn't come up in the formula. But of course, the conditional first passage times are much more complicated. Themes and variations. So what I want to talk about are some of the extensions I developed, which I'm biased because I did it, but feel that are not trivial extensions and aren't just producing unimodal curves. I have said that, but I forget now if there are more unimodal curves, so hopefully not, but whatever. Okay. So yesterday I spent a lot of time talking about encounter-based models, and there's something very subtle about it when you combine it with resetting. But let me just kind of quickly go through that and just remind you what I talked about yesterday. So look at the situation in which I have a single target, and when I'm inside the target, I build up contact time with the target, which is given by the Brownian functional, the occupation time, and I'm going to say absorption occurs once the occupation time exceeds some randomly generated threshold. So I talked about this a lot yesterday. Okay, and this is just reminding me about the ideas, just summarizing it. My stopping condition is that my occupation time exceeds a randomly generated threshold with distribution psi. I solve the problem in the case of a constant rate of absorption, but now with the extra twist, the constant rate of absorption is interpreted as the Laplace variable conjugate to the occupation time. And so if I invert the Laplace transform, I get the joint propagator for position and occupation time, and then I can use that to generate the marginal probability densities for a general absorption rule. Oops. Just remind you, and that's the picture I put up yesterday. Solve a classical boundary value problem, keep track of the constant rate of absorption, reinterpret it as a Laplace variable for occupation time, perform the inverse Laplace transform, multiply by your general threshold distribution, and you've got a general absorption process. Now let's think about implications for resetting. I mentioned this yesterday, but these are the explicit pictures. There are two ways you can imagine that you're maintaining information, because these are non-Markovian processes when size not exponential, of the amount of contact time and why that determines when you're absorbed. So one possibility is that when the particle is moving through your domain, it's affecting the domain and changing its internal state. When it's outside the domain, it just stays frozen. But each time it's inside the domain, it changes the internal state. That's a memory encoded in the substrate. But another possibility, and of course, so I was thinking about this. I was talking to someone at breakfast today, a mathematical physicist. She works on black holes. And I remember that I am trained as a mathematical physicist. And so I have this terrible habit I just like sitting and thinking. And I don't really care too much about whether people test my theories, which is a weakness of mine, but I understand now why I'm like that, because that's how I was trained. Because if you're working in string theory, you can never test it. And so one could argue maybe that's not science, I don't know. But I have this thing that if I have an idea which I think is cool, I come up with the kind of conceptual framework, but then I move on to another problem rather than going to an experimentalist and trying to convince them to test to see how feasible this is. So sometimes I'm asked in talks, so have you worked with someone to experimentally test your ideas? And then I quickly change the subject. But of course, it's a problem if you want to get grants, because you need to have an experimentalist on board. But anyway, so in my fevered brain, when I was thinking about this, the other possibility is it's the particle that has its state somehow changed when it's in contact with the substrate. When it's outside, it doesn't. And so it encodes the memory of the occupation time. So these two possibilities. Now, one of these has to occur which one experimentalists need to look at, but it has to be one of these two possibilities. Otherwise, there's can be no memory. Yeah, it could be a combination. Yes. Yeah, and probably that's the most likely scenario. Yeah. But the way I was thinking about it in this context is that now let's add reset. And this is why I think thinking about these problems in the abstract can be helpful, because it can at least organize ideas that maybe could be tested if someone was interested. Because if you have reset, it makes sense, at least in this abstract world, that you could not only reset the position, but also reset the internal state of the particle. And certainly this is the sort of thing one thinks about when one's looking at things like run and tumble particles, where you not only reset the position of the particle, but you also have to reset the allocation of the velocity state it's in. So it's not completely out of the blue thinking about this. Whereas if it was the substrate that changed, then it seems less plausible that when you reset the position of the particle, you're also resetting the substrate. It's a non-local process. The reason I'm banging on about this is that it's only in this scenario that we can use all these renewal arguments I've been talking about. So for example, if we now combine these two and look at this encounter-based model of absorption, I have this search process for this target. It resets several times before finding the target, but notice that whenever the particle resets its position, I also reset the occupation time to 0. And so you need to take that into account, but eventually you occur in a situation where you don't reset for sufficient amount of time that not only do you find the particle, but the state of the particle is such that it can be absorbed. If you look at the other scenario, it's a lot more complicated to calculate anything because you can't exploit the renewal process. So these are fundamental things and implications of resetting that I think is important when you look at more complicated processes you take into account. You can't just always think, oh, I reset the position and that's it. Anyway, so now this is what I was talking about with Luca this morning. He's very strict. He wouldn't even let me have lunch. So I anticipated that, so I had a cooked breakfast. All right. So, okay. You've missed all the best bit. Okay. So, again, thinking abstractly about what implications of reset and other situations, I've been motivated by synaptic transport problems of the effects of semi-permeable or permeable, or what would you say, partially permeable? Yeah, I'm going to stick with semi-permeable membranes. And so I started thinking about, well, suppose this could be inside a synaptic domain, because they're heterogeneous regions where you have structural proteins surrounded by a semi-permeable membrane. And then I started thinking about, well, what happens if you have resetting? It seemed to me a reasonable hypothesis that you only reset if you don't have to travel through the semi-permeable membrane. The semi-permeable membrane is an object that's there. And maybe one of the effects of the semi-permeable membrane, besides what happens to normal diffusion, is it screens from resetting. So the question I asked was, well, what happens if you introduce this idea? So the basic idea is that the minute you have screening by a semi-permeable membrane, you have heterogeneous resetting. You only reset outside the domain and not inside the domain. I've shown those curves again, sorry. And so then what I started to do was start exploring and analyzing the effects of the permeability on the mean first passage time, but also the effects of the interface radius on the first passage time and things like that. And, for me, it wasn't intuitive. So, for example, here, you'll notice the result that, so let me explain this a bit better. So let's go back, put some numbers to these things. So let's imagine spherical domain. I start off, x0 is on a sphere of radius r0. The semi-permeable membrane is a sphere of radius r1. and the target's the sphere of radius R2. Because this is the interface radius. So here, the target has radius 1. My initial position is at a radius of 3, and I'm varying the interface radius between the target and the starting position. And what I found was that if you're close to the target, you're very sensitive to the permeability of the interface, whereas as you move away from the target, so sorry, these different colored curves correspond to, for a given resetting, the variation of the mean first passage time. So the lower 3 curves are for r equals 1, the upper 3 curves are r equals 5. And what you notice is it becomes almost completely insensitive to the permeability when you're close to the starting position and far from the target. So using this mechanism, what seems to be occurring, I didn't find this very intuitive. You had to go through the analysis to explore this. There are interesting questions about the effectiveness of an interface and how it depends on the permeability depending on the geometry. So these are sort of questions you can start asking when you look at situations like this. And there's more I could say about this, but I want to kind of, yeah. Yes. It's not, but you have nicer pictures. And I say that semi-seriously because I forget if I mentioned yesterday, I've been criticized by referees when I look at 1D processes and I draw it. So I'm not exaggerating. I almost had a paper rejected because I was describing some stochastic process and I drew a particle like this. And the referee said, "Oh, how can you? You've drawn a 2-dimensional problem." And I try to say, "Well, you try drawing something along a single line. You can't show anything." So, I mean, yeah. So that was the level of refereeing on it was a physical reviewee. Yeah. So. But also, it doesn't have to be 3D. It could be 2D. 3D and 1D are very similar because you can do this trick of change of variables, V equals RU. But 2D, of course, qualitatively it's the same. But as I said, that's a much cuter picture than the 1D version. And the other thing I want to point out is that you can also apply the method I developed in terms of probabilistic interpretations of diffusion through semi-permeable membranes using this notion of snapping out Brownian motion. And the 1D case that was developed by a French mathematician, Leger, was obviously French and not English because he used the acronym SNOB. And yeah. So I modified it by calling it SNOB M for Brownian motion, because yeah. Anyway, so but just reiterating this, I can apply this problem to the screening situation in which I now break up my semi-permeable interface into 2 processes. Partial Brownian motion outside with reset. Whenever I hit the surface, I build up local time. When the local time exceeds some threshold, I stop the process. I don't kill it forever. I now throw a coin. Either I restart outside or with a probability of a half, I now start the process inside. Inside, I have no resetting, but I do have the possibility of terminating for once and for all because of absorption. By doing this, I can now generalize things further by taking the threshold probability for killing the process at each round of partial Brownian motion using a non-exponential threshold. So the whole counter-based theory can be applied to this quite complicated screening problem with resetting. Okay. So there's a lot of machinery, and then one of the things, of course, is someone doesn't want to just write papers for the sake of writing papers, is trying to think through what are interesting questions to ask using this. So there's 2 levels to this. There's developing machinery using renewal theory, strong Markov properties to deal with delays in resetting. and then thinking about geometric configurations and the effects of semi-permeable membranes, and using this snapping out Brownian motion to look at more complicated semi-permeable membranes. But of course, you've got to think about not just writing a paper, changing the configuration slightly and writing another paper. It's about using these methods and combining it with ways to think about interesting problems. And I'd contend thinking about, for example, the differences in whether the substrate or the particle builds up memory is one of those sort of interesting questions to ask, as is the effects of screening. Okay. The final topic, which will take a bit more work, is the following. And this is something I recently submitted, and it's to do with trying to think about a more complicated problem. So let me take a step back. I mentioned yesterday that one of the things I'm really interested in is a more target-centric viewpoint of search processes. Most, not all, but most search processes concern a particle, foraging animal, or a molecular motor, and asking what's the first passage time process whereby the animal finds a food source or the molecular motor finds a substrate to deliver resources. And there are two differences there, because in one case, in many, because the animal could be looking for shelter, but often it's looking for food to take from the target. In cell biology, because you're talking about differences in movement ecology and cell biology, I think a major difference in many applications in cell biology, you're typically transporting stuff somewhere. Whereas in a lot of animal foraging problems, you're foraging for something to take from a target. So two, it's not completely black and white like that, but there's a big difference. So I've always been interested in that kind of difference. And in this recent work, I've combined the two, in which a particle first has to find a target, which is let's not call it a source of resources, pick up the resources, and then deliver it to a target. And for simplicity, I'm going to just take this to be a diffusing particle, Brownian motion. I'm going to take this particle to be Trumpian, i.e. stupid, in that it never remembers where A and B are, but it does this forever. So it's a bit of a myth of Sisyphus, using as many cliches as possible in one sentence, of picking up resources, delivering it to a target, going back, picking up more resources. And the constraints are, number one, A has unlimited resources, at least over the timescales one looks at. And if this particle returns to A, excuse me, it doesn't collect more material. So the first time it reaches A, it picks up a packet of resources, and that's it. It keeps those resources until it finds B, delivers the resources, repeat forever. Okay, so that's the basic idea. So in this, black particle means it's empty. Once it reaches A, it becomes red, it's got stuff. And then once it reaches B, it delivers the stuff and becomes black again. And this repeats forever. Yes. But just as you can call something bouncing or bunched, Van Eyden in the NYU called it transition path. Yeah, but I think it's to do with the fact that, as I mentioned now, that one can now ask, well, so let me take again a step back. This sort of scenario, geometrically speaking, whatever, is identical to a chemical reaction landscape. So if you imagine now this is in some energy landscape for a chemical reaction, and in this landscape, this region of phase space represents the products for the reaction, sorry, the reactants of the reaction, and this represents the products. And you're interested in the rate at which, again, this can repeat once the products have occurred. It's a reversible reaction. You can go back to A. One would like to work out, well, what's the forward reaction rate of this process? In my case, what's the rate at which stuff's delivered to B? So in transition path theory, and this was developed by Van Eyden and Wienen, it's quite a very interesting theory. So they were working with an energy landscape, but I'll come back to that in a second. So the idea is you take some dividing path S between A and B, and you like to work out what's the rate at which paths cross? So remember, this is going on for all time. So over time, what rate are paths crossing S? But more than that, in order to have something that's relevant to a reaction, you don't take all paths. You don't take, for example, this path here, because, yeah, it seems to cross and go towards B, but in fact, it doubles back and goes to A. So that's not a useful path to count. So what you want to do statistically is just count paths that actually start at A and don't return to A before reaching B. They're called direct paths, and that's why they're called transition paths, and that's why it's called transition path theory. But this is a non-trivial problem, because what you want to do ultimately is count the number of paths. Let me show you a formula on the next slide. So what you want to do, you want to define your effective reaction rate in the chemical case, or the effective delivery rate of resources to the target, by taking a finite time interval minus t to t, counting the number of paths in this single trajectory that goes on forever, that cross and are direct paths from A to B, and divide by the time interval, take the limit t goes to infinity. Because you're taking a t goes to infinity limit, the way you can actually calculate this is use ergodicity. If your process is ergodic, there's a way of calculating this by calculating the probability density of these transition paths, the direct paths from A to B. And it's a non-trivial thing to calculate, but I'll kind of indicate some of the steps in a second. So that's the basic idea. You want a way of saying what's the probability, the density that anywhere, because you can then integrate along this dividing surface, what's the probability that anywhere on this dividing surface, a path that crosses this surface is a direct path from A to B, and you only include those. So it's quite a sophisticated idea. And the other thing you have to prove is that your result is independent of where you choose to put the dividing surface. So I could put it here, and you should get the same result for it to be physically meaningful. It's a beautiful series of papers and work that they developed. So I'm going to try to capture some of the things that are going on in this, and basically then tell you what I've applied it to. Okay, so let's assume that we have a stochastic process that has a well-defined stationary limit, rho x, and that this is an ergodic density. So the ensemble average with respect to this stationary density captures the statistics of this single trajectory that goes on forever. So I can replace trying to keep track of the number of direct paths and a single realization trajectory by a stationary density for the ensemble. And it turns out you can actually calculate this. Let's see if I can. Okay, so let's take a. So I have to introduce a few objects. So let's take a point that is not in A or B. So it's somewhere in the domain, the search domain. And let me define T minus AB to the supremum, the largest time before it reaches A or B. Okay. Yeah. So this is just saying this is the time. Is that right? Yeah. So if, let me say this a bit better. So if at time t I'm somewhere in the search domain, I define t minus, what is that? Yeah, t minus AB to be the time less than t where I'm still in the search domain. I haven't been to A or B. Similarly, t plus AB is the smallest time after t such that I still haven't reached A or B. So it's, if you like, the total time interval between either being at A or B. Okay. Then I define the following object. It's better if I look at my screen because, okay. So gamma is the set of all points at time t, such that they don't lie in A and B, and x Okay, so now I'm looking at trajectories. Sorry, I'm not explaining this very well. So I'm now looking at trajectories such that the trajectory starts at A and ends at B. So sorry, this is an abstract or mathematical way of just defining what a direct path is. It's a path such that it, at some point in the past, it was at A, and some time in the future, it's at B, but it's not at either A or B in the intervening time steps. Okay, so that's what all this represents. So it's easy to say it in words, actually, than in this case. Okay. So usually I find writing down mathematics easier to understand, but in some cases it's easier to say it in words. So it's kind of anyway. So then what we want to do, we define this density of direct paths from A to B through a point X according to this relation. So I've got ergodicity, but now rather than taking the full stationary density, I just take the density of the ensemble that captures, again, it's easy to say in words, the ensemble that captures the distribution of direct paths. So all of this is about making mathematically precise how I go from a single trajectory for all time, where certain parts of the trajectory are direct paths and the rest are not. So if we go back to this picture, so this is happening all the time. Here's an example with reset, because that's what I'm going to apply it to, with reset, which is a direct path. I start at A, in the intervening time, I don't go to A or B, and then before going back to A, I get to B. So what I'm trying to do is appealing to ergodicity and finding the effective density of probability that any point X, I'm on a path which is a direct path. Whereas rho of X, the full density, doesn't care whether it's a direct path or not. Because the contribution to, it's another way of saying it, if you're going from the time domain to the ensemble domain, I want to know what the contribution, the relative weighting of trajectories of my temporal system contribute to being at a position X. And that will be built up. So if you're thinking about stationary density, what does that represent? What represents the fraction, if you like, of paths that in a temporal domain pass through that point. So that's going from the time domain to the ensemble domain. And I'm now asking, well, if I'm at a point X, what's the probability that a path passes through X and it belongs to a direct path? Does that sort of make sense? Hope it does in words. Okay. If once one understands that, so of course, what you're doing here, you're just counting the periods of time in which you're on a direct path. This is in the time domain. Okay. And then this is the time average of this object, where you're just restricting to the times in which you're on a direct path. So you're filtering out the process. So you're only doing a time average over sections of your trajectory which belong to a direct path. And if you match that now to an ensemble average, this is the corresponding density. So that's what all that's about. It can be proven that, and I hate saying that in lectures because it's not trivial, but it can be proven that you can relate the ensemble density of direct paths to a point X in terms of what are called committer functions. And this is the guts of the theory. What are the committer functions? Well, the committer functions are the following. Q of X is a splitting probability. It's the probability that if I'm at X, okay, I've reached X such that I'm just trying to, you can see it's not easy to explain. Okay, yeah. So I'm at X, and it's the probability that at X, from X, so X is, if you like, an initial position in a first passage time problem. So I imagine starting in X, this is Q of X, and from X, I reach B before A. So it's a splitting probability, okay? So that's what Q of X is. It's a standard splitting probability where wherever I'm in X, in terms of this ensemble distribution, from X, I go to B before A. What about Q bar of X? Well, Q bar of X is the opposite. It says, if I'm at X, what's the probability that I came from A rather than B? So it's the reverse time process. If you reverse time, it will be a splitting probability. Okay. So let me kind of draw a picture. It takes a while, if you haven't seen this before, to get to grips. So I've got A and B. And I'm interested in this rho A, B of X. In order to calculate it, I need to know certain objects like Q of X and Q bar of X. What is Q of X? Q of X is the splitting probability that the process is such that if I start from X, I hit B before A. So it's directly the splitting probability of this stochastic process going to B before A. What about Q bar of X? Q bar of X says that it's the splitting probability, the probability that I reach X and I came from A rather than B. So if you reverse time, this is the splitting probability of the reverse time process that I reach A before B. And so this then becomes interesting because you have to study the reverse time diffusion process. And in terms of the original work with chemical reactions, the meat of it was that if you have a conservative force, so remember that it's a complex energy landscape, so you have a potential energy landscape. If your force is acting on the particle, which contribute to the drift term in your Fokker-Planck equation, if they can be written as a conservative force involving a potential, then you have reverse time symmetry. And the commuter function, in fact, Q bar of X is just 1 minus QX. It's like the forward process. However, if F is non-conservative, this is no longer true, and you have to do a lot more work to actually calculate what the reverse time drift diffusion equations are. So it's a non-trivial problem. In my situation, yeah.
Not saying I go from A to X, not Q bar.
Did I go from A? Oh, because you want to be focusing on this. Right, but you're ultimately interested in direct paths that are constrained to first go from A to here and then to B, and you need to have these constraints. And what this means is that you have to have it going from, it is going from A to X.
Yeah, say the Q bar.
Yeah.
Okay, I compute by considering that I go reverse and then I
yes.
But I'm saying, why not simply go straight compute from A to X without ever reaching B?
Oh, okay, because this could be a complicated space. I mean, if you, because now you have to specify what A is in detail, because remember, there are all these points inside. That's quite, I suppose you could do that in principle, yes. But what would the PDE for the boundary value problem be for this, where you're going from a set to a single point?
Yeah, but that's a point.
Yeah.
Once you have from a given point, then we integrate over initial points.
Right.
That's why. I mean, I don't see that difficult to do that problem. That's why I'm asking.
Yes, I don't know. Then my answer is that easy to do?
So the difficulty is, I mean, you don't have to read B. That's
right. Yeah. Right.
The initial point.
Yeah.
Over.
I don't know. So I haven't tried to calculate that. So it should be equivalent. But yeah. Okay. But whether, so I've never calculated, so I don't know how difficult it is to do. That's my honest answer. It must be equivalent, but the other way, certainly the other way leads to a boundary value problem, which is identical. Once you've backed out the reverse diffusion process, then it's a classical boundary value problem for a splitting probability, which one knows how to solve. And I don't know what the structure of this boundary value problem looks like, because you're going from a set to X. I don't know. Maybe
Otherwise,
it's
again, you have initial condition to another one, and you have many initial conditions. Then you just average over any of them.
right. Right.
Okay, so we can discuss later.
Yeah. But there is one thing. You have to take into account all the points inside A, don't you? Or you can start on the boundary? I have to think about that. I don't know. Yeah, there's a good point. Okay, Van Eyden's an idiot. He could have said that. I don't know. I don't know what the answer is. But that's interesting. So just stick with the forward process and just go from A to X.
And the Q bar, so the commutator just the Q bar.
Okay, so because I know you love, as I keep saying, the terms. So Q is called although it satisfies a backwards equation because it's a splitting probability, it's called the forward commuter function because it's forward in time, and Q bar is called the backward commuter function. Yeah. Right. All right. Okay. So that's why I wanted to spend some time with this. It's not so easy to explain. All right. So let me see. Okay. So on that point, we know how to write down. So now what I'm doing is before I was so rudely interrupted by Luca, what I was trying to say is that I am interested in the problem rather than in a energy landscape on just pure diffusion, but the resetting. And there are two aspects to the resetting process that complicate the problem. The first is, we go back to this diagram, the first is that resetting breaks time reversal symmetry. So that aspect of it, assuming that one can't, that it's more convenient to do this than, but actually I'll have an answer to you in a minute for something that I'll show you that in fact you can solve the things I want to solve without knowing the backwards process. You don't even need Q bar, which might be related to your comment, in fact. So the first thing is, if you follow Van Eyden's approach, you need to take into account that the backwards process is not time reversal. And that itself is interesting. How do you calculate the time reversal process when you have diffusion with resetting? But the other is, of course, now there are two ways that you can have a direct path that crosses the surface S. The usual way, where you just cross continuously, but now you can also cross by jumping to a reset point. So that adds complexity to the calculations. All right. So just to show you that things are quite different, this is what the boundary value of the operator is. This is the boundary value problem for the backwards commuter function, Q bar. When you look at the reverse time diffusion process, and it's with resetting, it took a bit to derive this. It's certainly very different from the forward equation. Oops. There are all sorts of extra terms that come up here. So I think that, I mean, in its own right, that's interesting just to study, because I don't think people have looked at that reverse diffusion process of resetting within this context. So that's of interest in its own right. Okay. Why? So that's just for the, if you're interested in the statistics of these direct paths, but I'm interested in first passage time problems, and quite interesting. So let me just focus on the first term. What Van Eyden and Wienen showed was that the reaction rate is given by the integrated flux through this dividing surface, where JAB involves these various terms. So you still need so at this level, you need both Q and Q bar, and you also need the stationary density. What I've shown is that because of the presence of these discontinuous jumps across the surface, there are extra terms, which are a bit messy, involving these two terms. So that's the first point. But yeah, so the first two terms and the JIB, this term is the same, but of course now you're solving Q and Q bar for the presence of resetting, number one, and number two, you replace the stationary density for the standard Fokker-Planck equation by this non-equilibrium stationary distribution or density that I talked about in the very first few slides. So that plays a major role in this theory. Okay. So it gets quite complicated, as you can see. And I think it's better to say things in words, I think. No, but to Luca's very annoying point, it turns out that you can actually rederive. It's annoying because I haven't got an answer at the moment, but it turns out that you can actually get you can prove this, that you can express the transition rate without needing to know the Q bar, which kind of speaks to the fact that maybe you can bypass that process anyway. And this is the formula. If you set R equal to naught, this is the formula derived by Van Eyden, where you replace this surface integral of the flux by a volume integral of the search domain, involving the stationary density and the derivative of your forward commuter function with a splitting probability with respect to x. Again, none of this is intuitive. It really is quite complicated calculations to get these, but this is the result. And then these extra terms, again, just involve Q and rho. They're the ones that take into account the effects of the discontinuous jumps across the surface. So it's quite a non-trivial problem. Okay. So let's apply this to a particular example. How am I doing time-wise? I'm almost done.
Yeah, overcome.
I've overgone. Okay, but that's your fault. Yeah. No. So let's just apply this to a particular example. So let's take the source to be an interval of size A, the target to be an interval of size B, and they're either end of an interval of length L. You can count, and I'm going to use the formula without Q bar. You can calculate everything explicitly and plug it in. You now need the non-equilibrium stationary density for the rho bar, which you can also calculate. So, I mean, I'm always terrible putting up formula no one's going to read, but this is proof by authority that you can calculate everything. But I said that I shouldn't put any more unimodal functions, but what I meant was unimodal functions are the minimum, but I'm allowed to show unimodal functions with a maximum. And so what I prove using these various results is that if you look at the this rate, I call it accumulation time because it's the rate at which stuff is being delivered and therefore accumulated at the target. If you plot this as a function of the reset rate, maybe not so surprisingly, there's an optimal reset rate in which you optimize the rate of delivery during this process. So it's a highly, in my opinion, a non-trivial extension of resetting. But wait to see what the reviewers say. They might say, oh, well, there's so many pages of resetting, we're not interested. But anyway, until that happens, I think this is a very non-trivial application of to a problem in resetting. But I think it raises a general interesting topic relevant to this conference, and that is thinking about these sorts of processes where you have you're combining both aspects of a search process, searching for resources, and then taking the resources and delivering it. Of course, one can now look at ramifications. One can say, well, now let's make it a bit more complicated. Let's introduce refractory periods that you don't instantaneously pick up resources. It takes time. So maybe you enter a stuck or bound or a bunch state in A. And similarly, it can take time to deliver the cargo. So you could introduce that into the system. Maybe there is some sort of memory that you need to include as well, because this is a very blind. But at the same time, one of the motivations for looking at a stupid particle is that if you had a situation where you have lots of resources and lots of targets, maybe it's no longer useful to actually detect or remember where the targets are, because you want to kind of spread out the resources. So kind of a completely stochastic random process might be more appropriate. And the other thing I should say is that when you think of cell biology, or even bacteria, detecting things costs energy. So if you have detectors, and this goes back also to bet hedging and things like that, that often just randomly switching a phenotype when you have a randomly changing environment can be more effective than actually having detectors that are looking out for major changes, because these detectors cost a lot of energy, both in terms of the genetics and so forth. So there are reasons why one might have a stupid particle doing this process. And I think I'll stop there. Okay.
Comments?
Yeah.
With the set value barrier and the resetting.
Yeah.
You look at that inside.
Yes. Yes. And in fact, when I was thinking about that, as I told Luca this morning, I was looking at your paper about the independence of, yeah. Yes.
So I have a question. So on when we had the refractory period and philosophy,
Yeah.
can you write? I mean, can you get to the probability or not? Can only to the mean?
Oh, well, not just the mean. I mean, you could get the moments.
So,
Yeah, because it's just the generator. You just take higher derivatives. You can get the, yeah. Can you, so you want the full first patches time
yeah,
in time? I have no idea. I don't try, because I don't want to start inverting Laplace transforms, so I stick in the Laplace domain. So I think maybe in 1D it might be possible to, but I haven't done it myself. I mean, Krebenkov might have looked at that in some of the resetting. So I know some people have pulled out the time dependent. Yeah. 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 So with the refractory, I don't know. I don't know. Yeah.
Okay, thank you so much.